Really? Okay. So if I look at the syllabus one more time, let me remind us where we are. We finished that part, and yes, we need to look at chapter 7. This is where we are right now. So chapter 7 is what we need today. Monday next week, we have a review for the second test. That second test is on chapters 5, 6, and 7. So that's the arrangement. And then, once we're done with that, we start the last part of the class. Again, the final examination is not comprehensive. The final is just going to cover the remainder, chapters 8 and all the way. So the second test will cover 5, 6, and 7. And today we need to look at chapter 7 and we deal with that. I have somebody's question before we start this thing. Let me see. Somebody was asking, let me first do this. I think I better do this to begin with. I want to answer somebody's question about chapter, I think 5, how to find the percentile. Let me bring it up and we see. Okay. Oh, come on. I don't want green. I don't want green. Green color is not good for me. Okay. So here is a question from somebody's homework. I promised to look at it, and I think here it is. It says that the age of children, let me copy that thing and push it in here. So this is from chapter 5, I guess, which says that the age of children in the kindergarten is uniformly distributed between 4.74 and 5.78 years old. A first-time kindergarten child is selected at random, round to 4 decimal places. And this person was wondering how to do part E. Let me just go ahead and look at part E only. I think the others are okay. If such a child is, so this was okay, everything was appeared to be good here. Let's check out part E. If a child is at the 23rd percentile, how old is that child? And here's what they mean by that. Let me draw my picture, which represents the uniform distribution. So to begin with, you want to have your uniform distribution, which begins at 4.74 and ends at 5.78 right here. And anytime you hear the word uniform, remember there's a rectangle. There is a rectangle which represents the situation, okay, where the height of that rectangle is what we call the f of x, or the function value. So when I look at the height is always going to be 1 over b minus a. Whatever b is the number to the right, 5.78 minus 4.74, and that is 1 over 1 point, is it 1.4? I think if you subtract, yeah, that should be 1.14.
I think it's 1.04.
04, you're right, thank you, 1.04. So the height of that rectangle is 1 over 1.0. Now, here's what they mean by that question. They want you to find a value, okay, yet to be determined. But that k, which you don't know just yet, is such that the area to the left of that k is the given percentile. And that area, my laptop is not behaving well, so. And that area is 0.23. because it is talking about the 23rd percentile. So in essence, you're asking yourself, what must K be so that the area which I've shaded is equal to 0.23? And to recover that K, let us first start by asking ourselves, how do we find the area of that thing? Well, that area, let me first move this stuff here. If I want to find that area, we find the length of the rectangle. So K minus 4.74. That is the length of the rectangle, but the height is the same. So times the height, which is 1 over 1.04. And we know that area to be 0.23. So you set up that kind of situation and find out how that K should be to make sure that your area is 0.23. Well, this is K minus that. So what I have to do is to multiply both sides by 1.04. I multiply both sides by 1.04. So that disappears on the left-hand side. And when I do that, I have K minus 4.74 on the left-hand side to be equal to 0.23 times 1.04. See, when I multiply on the left by 1.04, they disappear. When I multiply on the right, that's what I'm going to have. So K minus 4.04 is, if I pick up my calculator and I have 1.04 times 0.23, yep, 1.04 times 0.23 is what I meant. Jeez, I can't even type on my calculator.
0.2392.
Okay, times 0.23. Yeah, 0.2392, 0.2392. And then of course, you add the 4.74 to both sides because you are trying to isolate the K. You're now solving, you're now adding 4.74 to both sides, leaving you with 4.9792. How many decimal places? That's what it is. So that's the K. That is the value of K, which will give you an area of 0.23 because of the 23rd percentile. So that's what you do to isolate that unknown value. You work backwards. So previously, you are finding the area, but now that you know the area, how do you go back to find that K, which gives you that area? And that's what you do to find that K missing. All right. So regardless, many questions really ask you for that. They give you the percentile and they want you to go backwards and find the missing link in the equation. And so we use some kind of algebra to really go backwards and we find it as it were. All right. Okay, so now let's go to chapter 7. Chapter 7 is a good application of what we call the normal distribution. It is an application, a use of the normal distribution. And we call it the Central Limit Theorem. Central Limit Theorem, CLT. So here's the thing. Here is the general overview of what is happening. If in the medical field and so many other places, what they do is they normally do not track down individual items in the population. What I mean by the following is that, in fact, a good example is look at the COVID going on right now. So if they administer a vaccine to maybe pregnant mothers. They do not look down at each mother and determine how she is doing or performing. In other words, if they are so they don't, okay, when they administer the drug to individual mothers who are pregnant, they don't monitor them one after another. So what they do is they administer the drug to maybe a group of 40 mothers. They administer the drug to another group of 40 mothers. They administer the drug to another group of 40 mothers, right? And then what they do is maybe if they want to know the average time, the average number of mothers who registered maybe a problem or had a headache or something like that. So they find the average in the first group, they find the average in the second group, they find the average in the third group. So they monitor the groups, they monitor averages, they look at groups, they monitor how the groups are performing, not really individual people. You know why? When you monitor groups as opposed to individual items, the variability is reduced. You reduce the variance, you reduce the spread. So this is the so-called tracking down groups, tracking down averages, as opposed to tracking down individual items in the population. That's a very good, big deal in statistics, whereby you, instead of looking at the individual performances, you look at groups. When there's a new testing program for SAT, to prepare people to take the SAT scores in high schools, they don't look at individual performances, they look at averages. What was the average performance for the first 20 group, the average performance for the second group, etc. So they know the averages, not really individual people. I hope that is making sense. So to cut the long story short, the central limit theorem is a way that we can monitor groups as opposed to monitoring individual items. So to that end, there are two versions of this thing they call the central limit theorem. There are two versions. The first version is what we call the central limit theorem for means. And here's what they do. You start with any population with a known mean and known standard deviation. The population may not be, it may be normal, it may not be normal. And then you take all possible samples of a given size. Like I was talking about, maybe a size of 40, a size of 40 here and there. And for each sample, you compute the sample mean, the average of each group. So what happens? You end up with a collection of means, a collection of sample means, which I'm labeling X1 bar, X2 bar, all the way. Maybe there are 1,000 of them. So to come back to what I was talking about here, you find the first group, you measure the average in that group. The second group, you measure the average in that group all the way. If these are ages, you find the average age. If these are heights, you find the average height. If you are tracking down IQ scores, you find the average IQ score for each group. And so the question is, how are these averages behaving? Can we say something about these averages? And it turns out that this sample means will follow a normal distribution that is huge. They will follow a normal distribution as the sample size increases. By the way, the mean of these sample means coincides with the mean of the population. This is the symbol we use to designate the mean of the sample mean. When I write mu of X bar, I mean the mean of these means now. Coincides with the mean of the population. And the standard deviation of these sample means is given by this formula here, sigma where sigma is the population standard deviation divided by the square root of the sample size. And as you can see, the variability is reduced. If you have sigma and you divide by root n, you are reducing the value of the standard deviation. So this is what we're talking about here. In other words, after you collect these sample means here, after you have a data set of sample means, if you create a histogram of those sample means, you're going to end up with a barrel shape like this one. You're going to end up with a barrel shape like this one. So this is what I mean by the normal distribution. If you look at the sample means will end up being normally distributed. All right. In other words, the mean of those means coincides with the mean of the population, and the standard deviation is obtained by grabbing the standard deviation of the population divided by the square root of the sample size. That's what we're talking about here. So symbolically, here's what we write. When you see this thing that I'm circling, boxing up here, we are saying that the sample means follow a normal distribution, the mean of which is the same as the population mean, and the standard deviation is obtained by dividing the population standard deviation by the square root of the sample size. So if the population standard deviation was 5 and the sample size was 25, then sigma over root n is 5 over root 25, which is 5 over 5, which is a 1. So the sample means have a smaller standard deviation of 1 as opposed to being 5 in that case. And in statistics, if you have a data set with a smaller standard deviation, the values, the results from such a data set are more consistent because the variability has been reduced. So that's why many times studies prefer to track down groups and not individual items in the population. What we call it, the central limit theorem for the mean. The second version now is the central limit theorem for the sums. Well, imagine if you did the same thing, the population with mean, mu, standard deviation, sigma. You take samples of a given size like we did before, but instead of looking at sample means for each group, you add up all the values in each group. You find the sum of the items in each sample. If there are edges, you add up the edges in each group. If there are IQ scores, you add up the IQ scores in each group. You end up again with another data set of sums, values, each value from a sample. And it turns out also that this set of sums becomes approximately normally distributed. And the mean this time is n times mu. You multiply the sample size by the population mean, whereas the standard deviation is obtained by multiplying the the square root of the sample size by the population standard deviation. So in other words, we have two normal distributions. This was from the sample means, this is from the sums. And that is it that there is about this chapter. So this chapter is about these two normal distributions. Now that we know how to work with a normal distribution, we are going to be answering questions that relate to these two normal distributions. That's what it is. This is what we call the central limit theorem. Again, you track down groups. You track down groups of salmons in the ocean, group of homes, groups of, I don't know, whatever it is, group of plants in the corn plants in the cornfield, people, name it, fish, lions. You track down groups and not individual items. These are the two normal distributions that we create. Now, before we start some information, let me put a few fillers here. At the beginning, I was saying that you track down, you take samples of a particular size. Well, here's what happens. If the population from which you are taking samples is already normal, then the sample size can be any value. What I'm saying is, if the population from which you're going to take samples is already normal, there is no restriction on the sample size. The central limit theorem is going to work regardless of the sample size. However, when the population is not normal, for you to attain the central limit theorem, you need a sample size bigger than 30 or more. So 30 is the magic number that you need to attain the central limit theorem. If you are taking groups from a population that is not normal, but if it is normal already, who cares about the sample size? 10, 20, 35, the central limit theorem will be satisfied in that regard. Okay? Check this example out. An unknown distribution has a mean of 90 and a standard deviation of 15. Samples of size 25 are drawn randomly from the population. Find the probability that the sample mean is between 85 and 92. Check this very carefully. They are saying you have a group of means. What is the probability that you can have a sample with a mean between 85 and 92? And then find the value that is 2 standard deviations above the expected value of 90 of the sample mean. So the thing here is, we are back at the normal distribution. We are going to use the normal distribution like we used it in chapter 6, except it's going to be done from the central limit theorem point of view. So the thing here is, we don't know anything about the original distribution. However, because we are taking samples of that size, we know that these guys follow a normal distribution. With this kind of information, that suffices for us to find what is happening. So this is what we know. X bar follows a normal distribution with mean mu, standard deviation sigma over root n. Let us find what those values are. Let us find out what these guys are. The mean is the 90 that we are given here because you are told that the mean is 90. The standard deviation of the population is 15. So we grab the 15 and we divide it by the square root of the sample size, which is 25. So because this is a 5, 15 divided by 5 is 3. So here is what we have. This is now describing our normal distribution fully. And anytime you have a normal distribution with a mean standard deviation, you can find anything. So in fact, here's my picture. The mean is 90. I want to know the area which is located in that in the middle there from 85 to 92. And then what do? I go back and find my normal distribution, don't I? So let me go and I bring up this normal distribution like we used it. I'm sure now you are very, very confident in using the normal distribution calculator. So let me go to chapter 6 maybe, and I bring it up. We shall look at chapter 7, some exercise chapter 7, but let me bring up the normal calculator as we know it. Chapters, we used it in chapter 6, here it is. We used it here. The normal calculator. This is what I'm talking about. So if you are asking me to find this area, well, what do? We do what we did before. You look at the mean, identify the mean. The mean is 90 here. 90. What's the standard deviation? The standard deviation is not 15 anymore. The standard deviation is 3. And then what do you want? Because it's going to be in between two values, you select x1, x2. You put 85 here. You put 92 over here. And you'd say, okay, I want it. What is it? And this guy is going to give it to you right here. The area is 0.6997, which is what I have here. This was using the TI-84, but I'm saying we have this online calculator, which can do wonders for us as well. There's no need to go and grab the TI-84 if you have this free thing. So the thing here is we are going to be concerned with describing this normal distribution and then going to the calculator to find the required areas as such. The second part was find the value that is 2 standard deviations above the mean of 90. Well, we know that this sample mean is for this normal distribution. The standard deviation is 3. If you're going to go 2 standard deviations, this is what we're talking about here, down here. Multiply 2 by the 3 to make it a 6, and you add it to 90. So it's 96. So in other words, from 90, if you go 2 steps, you jump 1 step, and the second step, each step of which is 3 units, you're going to end up at 96, right? Okay. The length of time in hours it takes an over 40 group of people to play one soccer match is normally distributed with a mean of 2 hours and a standard deviation of 0.5 hours. We take a sample size of 50, find the probability that the sample mean is between 1.8 hours and 2.3 hours. So what you do is you try to describe the normal distribution that you want. The sample means will follow a normal distribution with the mean 2 and the standard deviation sigma over root n. X bar follows this. And you have all the information. So the mean is going to be 2. The standard deviation is going to be, if you put this thing in the calculator, this will be, let me see. This will be, I grab 0.5 divided by the square root of 50. You end up with 0.0707. That is the new standard deviation, which you grab and put back here. So this time the mean is 2. So the mean is 2. The standard deviation is 0.0707. And you want to go between 1.8 and 2.3. 2.3. And you say, what is it? 0.9976 or 77. That's what it is, 0.9977. In a recent study reported October 29, 12, on the Flare blog, the mean age of tablet users is 3.4 years. Suppose the standard deviation is 15, and you take a sample of 100. You take groups of 100. What is the mean and the district and the standard deviation for the sample mean ages? There it is. The mean is the same as the population mean. The standard deviation is always what? Sigma over root n. Sigma is 15, n is 100, so the standard deviation is 1.5. What does the distribution look like? Approximately normal. You end up with a bell curve. That's what the standard deviation will be, and it ends up being an approximate normal distribution. Part C, Find the probability that the sample mean age is more than 30 years. Okay, this is what they are talking about. They are asking for the probability that the sample mean is bigger than 30. So look at my picture. I got the normal distribution calculator again. The mean is 34 here. The standard deviation is 1.5. And I want to go to the right of 30. So I'm going to select only the first item, the X1 here. I put 30 here. And I say calculate. And make sure you look for the right one, because it gives you both to the left and to the right. So you want to make sure I really know what is happening. I want to go to the right, so it is 0.9962. 0.9962. So that's the area. So the normal distribution calculator is back. We're just using it in the context of the central limit theorem. Can we also find percentiles? Yes, we can. Find the 95th percentile for the sample mean. So one more time, they are saying that imagine if you have this normal distribution, the mean is 34 right in the middle. What is that value K for which the area to the left is 0.95? If you are using a TI-84, this is what you do. But let me bring up my calculator one more time. So because you're looking for the 95th percentile, what you do on the pull down menu here, you select the second option. P, X bigger than little x1. You are now going to find the little x1. In other words, you put the area here. Don't put 95, put 0.95. And you say calculate. And you see this picture that I have here is similar to what I have in the calculator. Matter of fact, if I come down here, the value is 36.467 something. Because it's saying that the probability of going to the left of this number is 0.95. So that's the 95th percentile, 36.467. So the only thing that is changing is making sure that you modify the normal distribution. Otherwise, you bring your calculator and the same things that we did in chapter 6 are back here. Okay, now for the sums, where look at this example. An unknown distribution has a mean of 90 and standard deviation 15, a sample of size 80. A sample of size 80 is drawn randomly. Find the probability that the sum, you see, mark the words, the sum now, not the mean, but the sum. The sum of the 80 or the total of the 80 values is more than 7,500. And then find the sum that is 1.5 standard deviations above the mean of the sums. So now we are talking about the second central limit theorem that tracks down sums. We found out that the sums, which are designated by writing sigma x, follow a normal distribution, the mean of which is n times mu. What is n? N is 80. What is mu? Mu is 90. 7,200, which is the mean now. And the standard deviation is root 80 times 15, which becomes 15 times square root of 80, 134. So this is 134.164. 1641. If you're using the TI-84, the good thing about the TI-84 is that you don't have to, find this. You just type it as it is. You just type root 80 times 15, and the machine is going to take it. But with this online calculator, I'm finding it out because I need to type it as it is in the calculator. Now, what do we want? Find the probability that the sum is more than 7,500. So the mean is 7,200 here. And 7,500 is going to be to the right of 7,200. And what you are asking is the area that is shaded in blue, the area that is shaded. So I bring back my calculator here. I change the mean to 7,200. I type in the standard deviation, which is 134.1641. And I want to go to the right of 7,500. So I'm going to pick the first value, 7,500. And I say, calculate. It takes a while because these are big numbers. I think we saw this last time, but you have to be patient, wait for it. There it is. So to the right of 7,500 is this second option. Probability X bigger than 7,500 is 0.0127. Okay, so that's the answer right there. And as you can see, the area is to the right of that value, very tiny area, which is given to you in that portion. So you want to make sure that you really select the one that is consistent with what you want to find. So apart from changing the values of the normal distribution, the mean and the standard deviation, we are just back at the same kind of information. The sum that is 1.5 standard deviations above the mean, where the mean is 7,200, the standard deviation is that much. So what we do, I multiplied the standard deviation, which I think was what, 134 point something, 41 by 1.5, okay, and then you add it to 7,200, you end up with the 7,401. So this value, 7,401, is 1.5 steps from the mean, where a step is measured as 134.1641. All right. The same problem we had of tablet users. Suppose the standard deviation is 15, you take a sample of size 50. What are the mean and standard deviation for the sum of the edges of tablet users? And what is the distribution? Well, these are sums. The mean is mu times n. 50 times 34 is 1,700. The standard deviation is the square root of 50 times 15, which is 106.06. So this is the mean, this is the standard deviation. And it is approximately normally distributed. The distribution is approximately normal. And then part B, find the probability that the sum of the edges is between 1,500 and 1,800. So like I always do, I prefer to have a small picture describing what I'm talking about. So I have this normal distribution. The mean is 1,700. I want to know the chances of getting a sample with a sum between 1,500 and 1,800. Well, let's see. Let's take it away. The mean is changed to 1,700. The standard deviation is changed to 106.06. And I would like to be between two numbers. I select X1, X2. The first one is 1,500. The second one is 1,800. And I say, I want it. Again, these are huge numbers. We have to wait for a little while. It's gonna come up. It's gonna come up. Okay, there it is. And it is the probability of being between 1500 and 1800 is 0.7974. 0.79, this should be 7975. This should be 775. This is a 7 here. 0.797. Yeah, so really it is the same old stuff with the normal distribution. You just have to make sure that you really know what is happening. Part C, find the 80th percentile for the sum of the 50 edges. So now they are asking for the value K, which leaves an area in the left of 0.80. So one more time, you come over here, same mean, same standard deviation. Switch this to the second option and put the area here, 0.8, and calculate. Wait for some time again. It works, it does a lot of work in here. 1789. 1789 it is. So the value of K is 1789, meaning that the area to the left of this value is 0.8. All right. So the rest really are discussing the use, because I want to really, okay, let me check this one out, and then we move on to the third part. The mean number of minutes for app engagement by a tablet user is 8.2 minutes. Suppose the standard deviation is 1 minute. Take a sample of 70. What are the mean and standard deviation for the sums? Find the 95th percentile for the sums and interpret this value. Find the probability that the sum of the sample is at least 10 hours. Same thing. Well, these are sums, right? The mean is n times mu, where n is 70. N is the sample size, 70, times the standard deviation, or times the mean of 8.2. If you multiply 70 times 8.2, you get 574. That is the mean of the sums. If you pick all the sums, this is their average, the average of the sums. The standard deviation is the square root of 70 times 1, because you are given that the standard deviation of the population was 1. How about 8.36? Okay. The 95th percentile is the same thing now. So I go back to my calculator. I put in the mean. Oh, come on. I have a new mean, which is 574 here. 574. The standard deviation is 8.36. 8.36. And I want to go for the 95th percentile. So I put here 0.95. And I say, what is it? It's going to be 587. What is it? 587 point a bunch. 587.75 or 76. Or because, the reason the decimal is not working out here is because I think the rounding, finding the standard deviation was rounded up. But it's the same process we used. Now, when he talks about the probability, find the probability that the sum of the sample is at least 10 hours. Guess what? This information is in minutes. So when he talks about hours, it is only important that we change the hours into minutes. So this is asking for the sum of at least 600 minutes. By the way, what does at least mean? at least means more than. So this is the probability that the sum is bigger than or equal to 600. Yeah, at least something means something or more. So we want the area to the right of 600. So I'm gonna come back here. I select the first option. I put 600 here and I calculate. So the area is very, very small. It's right here, 0.3094 and so on, 9352 and all that kind of stuff. Okay. So this is what happens. It's all about identifying the normal distribution that you need to use, and you're in business. Again, it is the normal distribution. The issue here is, what do you have? Are you going to use the central limit theorem for the mean or the sum? There are two normal distributions we are creating. Okay. So now, this example, let's go through this example very, very carefully. A study involving stress is conducted among the students on a college campus. The stress scores follow a uniform distribution. Yeah, you had that. The stress levels follow a uniform distribution with the lowest score of 1 and the highest score of 5. So in other words, X from chapter 5. Welcome back, chapter 5. That's what this is talking about. A mean of, the lower value is 1, the upper value is 5. That's the uniform distribution. So the population is uniform. The population is not normal. But look at, then what do we do? We use samples of say 75. You pick a sample of 75 students. What is the probability that the mean of the 75 is less than 2? What is the 90th percentile for the mean score? Look at part C. What's the probability that the total of the 75 is less than 200? And what's the 90th percentile for the total stress score for the 75 people? So we are beginning with the uniform distribution. Then we take groups of 75, and we are now going to use the central limit theorem in big, in its own, in real sense here. So really, problems A and B ask you to find the probability of a percentile or a mean, whereas problems C and D are asking you to find the probability or a percentile for the sum. But we know that the individual stress scores follow a uniform distribution where A is 1, B is 1. Can we find the mean and the standard deviation of the population? The answer is yes. When you have a uniform distribution, the mean is the average of A and B. So 1 plus 5 divided by 2 is going to be 6 divided by 2, which is 3. The standard deviation, remember, is this formula. You can also look at it as B minus A over root 12. That's a formula we use to find the standard deviation for a uniform distribution. Now, this is the mean of the population. This is the standard deviation of the population. But part A is asking for the probability that the averages are less than 2. So this is what you're talking about here. Find the probability that the sample mean is less than 2. But from the central limit theorem, the means follow a normal distribution with mean mu and standard deviation sigma over root n. So we now have to find these numbers. Well, mu is the mean of the population, which is 3. Okay. Sigma over root n is what we need. So if I pick 1.15, I need to divide it by the square root of 75 because the sample size is 75. So really, this is normal 3 and 0.1328. So we have created a normal distribution. We began with a uniform distribution, but we have created a normal distribution. And now we are ready to answer anything about this normal distribution. In particular, the chances of finding a sample with a mean less than 2. Well, let's come here. The mean is 3. The standard deviation is 0.1328. And you want to go less than 2. And you know what? This is interesting. What does this mean? Probability x less than 2 is 2.536, and then there is E14. It is 2.53, 2.53686. And then there is E. If you get this kind of answer on the calculator, do not tell me that the answer is 2.53. You know what this means? This is what we call scientific notation. This item, this addendum here, this number was so small that it couldn't fit on that calculator. They wrote it in what we call scientific notation. This E, -14, means move this decimal point to the left 14 locations. So this is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and then the 2. And imagine how small this number is. That's why this is a 0. This is practically 0. This is, forget about this, just a 0. So a probability is never bigger than 1. So don't tell me that, you know, I saw 2.56 and that's my answer. It is not a probability. It is a very, very small number. When you see this kind of stuff, this negative means you're going to move this decimal point wherever it is. So first of all, the decimal point is right here. You grab it, you move it to the left by as many locations as this number is telling you. And that's why the answer is practically 0. What does this mean? Let me go back to the problem and we put this thing in context. It says the stress score. In other words, if you pick groups of 75 people, yes, I know that each individual stress score lies uniformly between 1 and 5, right? But what they are saying is that if you take a group of 75, if you take a group of 75 students, there is no chance that the average stress score is going to be less than 2. The average stress score for the 75 students is never going to be less than 2. So if you take the stress scores and then take the average of the 75, there's no way it's going to be less than 2. That's what this is talking about. Okay. Part B, the 90th percentile for the mean score. Okay. I go back here. Since I want the 90th percentile, I go over here for the second option and I put 0.90. Calculate, and here it is, 3.17. In other words, 90% of all groups of 75 have an average stress score less than 3.17. I mean, we are back to the same interpretation of the normal distribution. Well, how about part C? Part C and D are discussing the sums, the probability that the total, the word total says it all, that the total of the 75 scores is less than 200. Well, from the central limit theorem, the sums follow this kind of normal distribution. Let us populate these values and we see what is happening. N is 75, mu is 3. If I multiply 75 by 3, I get 225. When I multiply 1.15 by the standard deviation, 1.15, okay, sorry, 1.15 times the square root of 75, I get 0.1328 again. I think this is what we got before. Okay, and then I go back to my calculator and I change my values for the normal distribution. This time the mean is 225. The standard deviation is 0.1328. And I want to go to the left. So I go and pick the first option, put 200 here, calculate, and there it is. 0.006, I have a 0. I think it's almost the same thing here. Is this what I had? Let me see. Did I get it? 1 point, no. Yeah, okay, 1.15, you're right. Times the square root. Yeah, we are good, of 75. Yeah, 200, we are good. So 1.328, yes, 0.1328. Less than 200 is really 0. It should have been something, I don't know. That's not too good. 225, 0.1328. Let me add some more stuff here and see what happens. 0.1327905619. Let me see what happens if this can change a little bit. It doesn't. It's really 0. So it is 0.006, but it's really 0. So there's no chance. It is telling you, if you take a group of 75 and you add up their stress scores, the likelihood of having a group with a total less than 200 is not there, is 0. And then the 90th percentile, we are back again to the 90th percentile. For the same information, I pick the second option. I put 0.90 and I will get 225. What am I doing? I think I put in wrong information, right? How can this 225? Why am I getting different values? 90th percentile, 3 times 75. Am I right? How come this is not giving me some wrong numbers here? Why? Let me see. Normal distribution, the mean is 225. Is that true? 75, I'm sorry. 75 times 3, 225, yes. And 1.15 times the square root of 75 is, oh man, I think I messed it up here. I don't think this is true. I messed up actually, that's why it is getting. When I multiply, I think I messed up. When I multiply 1.15 by root 75, this is not what I get. I think this is 9.9593. I think I was dividing instead. So if I go back here, no wonder I was not very comfortable with that value. 9.9593. And if I want to find the area to the left of 200, yeah, this is it, 0.006, which is what I have over here. So I was putting in a wrong standard deviation, guys. I'm sorry. I wasn't multiplying as I should. Now, the 90th percentile, now that we have the right standard deviation, I put 0.9 there, and I should have 237 or thereabout. And yes, that is it, 237.76. So this is what we call the central limit theorem, guys. Everything else here is almost the same. I want us to go to, let me try one more before we go to the homework questions. That's where the action is. In the US, someone is sexually assaulted every 2 minutes. Isn't that terrible? On average, according to a number of studies, suppose the standard deviation is 0.5 and the sample size is 100. So we don't know what the distribution of the population is, and that's okay, because we're going to take samples of 100. Find the mean, find the median, the first quartile, and the third quartile for the sample mean time of sexual assaults. Find the median, first quartile, and third quartile for the sum of sample times of sexual assaults. Find the probability that a sexual assault occur on average between those two numbers. Find the value that is 2 standard deviations above the sample mean. Find the interquartile range for the sum. So let's go and build our normal distributions. Use the central limit theorem for sums for part A. Why? Because it says find the mean and all that for the mean time. But we know that the sample means for this normal distribution with the mean mu, the same as the mean of the population, and the standard deviation is 0.5 over the square root of 100, which is 10. So this is our new normal distribution that we're gonna use. Now, if he wants us to find the median, by the way, when you have a normal distribution, the mean is equal to the median. The mean and the median are always the same in the middle. Let's go back to what he wants us to do. He says, find the first quartile and the third quartile. Well, what does first quartile mean? Q1 is the 25th percentile. And Q3 is the 75th percentile. So if I look at this picture, those are the two things you are missing. What are they? We want a value which leaves 25% to its left. We want another value which leaves 75% on its left. And this calculator we have here can give us those two numbers in one go. You know what you do? I think we did use a little bit of it, but you come here, you put the mean is 2. You put the standard deviation as 0.05. Is it 0.05? Yep, 0.05. And you can get these two numbers in one go. You know what you do? Come down here and select P1, P2. Select P1 and P2. Put the first probability here, 0.25. Don't put 25. Put the second probability here, 0.75. The machine is going to give you the two values, one of which leaves 25% in the left, the other one will leave 75% also in the left. And here they are. So the first quartile is 1.9663. The third quartile is 2.0337, which are right over there. Matter of fact, the picture says it all. What the heck is this? I don't know what. This is a very funny picture. I think it just, it breaks it up in a funny way, but you know, whatever. So we have 1.96 somewhere here, and we have 2.0337, which are the values you're looking for. So this is how we can find those two guys using this calculator. You could have done it piece by piece. If you wanted to do it one at a time, you'd go for the second option here and just put in 25%. You're gonna get the 1.996 right there. And then you would put in the second value here, 0.75 independently, and the machine will also give you 2.0337. So those are the first and third quartiles. All right. They want us to find the same guys for the sum this time. So we first of all update our mean and standard deviation, because you are dealing with the sums here. N, which is 100 times 2, is 200 here. That's the mean. Square root of 100 is 10. 10 times 0.5 is a 5. So those are our new parameters. So I come here, I make it 200, and I make this a 5. Then I go for P1, P2, 0.25 and 0.75. And I have my values here as 196.62 or 63 and 203.37 as Q1 and Q3. Again, the median is the same as the mean here in the middle, because the mean and the median always agree for a normal distribution. Okay. Find the probability that the sample mean can be between 1.75 and 1.85, where use the mean and standard deviation for the central limit theorem, which was a 2 here for the means, and this is 0.05. You want to go between two values, so you go for x1, x2, 1.75, 1.85, 0.0013, 0.0013. That's the probability of having a sample with a mean between those two numbers. And then the other guy here is asking, what value is 2 standard deviations above the sample mean? what value is 2 standard deviations above the sample mean? We know something. It's what we know. The mean is 2, the standard deviation 0.05. So if you want to go 2 standard deviations above the mean, you want to multiply 2 by that standard deviation, and you add it to 2 above the mean. So that's the number which is 2 steps beyond the mean. The interquartile range is always Q3 minus Q1. That's the meaning of the interquartile range. And we have these numbers already. For the sum, where are they? They are right here. 203.37 minus 196.962, 6.75 is the interquartile range, which is the same as the middle half. In the middle, 50% in the middle. All right. So this is what we have. I mean, I think this is also almost the same thing here. Let me go look at it. A study was done about violence against prostitutes and the symptoms of post-traumatic stress that they developed. The age range for prostitutes was 14 to 61. The mean was 30.9. The standard deviation was 9. In a sample of 25, what's the probability that the mean age is less than 35? Okay. Is it likely that the mean age would be more than 50 years? Then in a sample of 49, what's the probability that the sum now? Okay. What's the 95th percentile for the mean, and what's the 90th percentile for the sum? So the same stuff that we're talking about is back here. So I first of all build up my normal distributions. The sample means follow a normal distribution with the same mean as the population, but the standard deviation is scaled like that. So the mean is 30.9, the standard deviation is 1.8. And I want to go to the left of 35 because this is what it's talking about. So go to the normal calculator, update the mean and the standard deviation 1.8. And you want to go to the left, you pick the first option, put a 35 here and say, okay, what is it? 0.9886. So 98%, about 99% of all groups of 25. This is very interesting. If you take groups of 25 prostitutes, 99% of all the groups of 25 prostitutes will have an average age less than 35 years. And yet, individually, they range from 14 to 61. But what is this person doing on the street? 61 years old? But anyway, the range of the individual prostitutes goes from 14 years all the way to 61. But this is saying that if you take groups of 25 prostitutes and find their average ages, 99% of them will have an average age less than 35 years. So this is could be necessary, important information to some, psychologists or whatever it is that are studying this stuff, Part B, how about finding, what are the chances of finding a group of 25 with an average age more than 50? Well, let's find out. More than 50, I'm gonna put a 50 here, and I say calculate, and more than 50 is 0. There's no way. There is no way you're gonna find a group of 25 prostitutes with an average age more than 50. That is, of course, there's no way, you know. That's what the thing's talking about. And then part C, what's the probability, if I go back here? In a sample of 49, what's the probability that the sum of the ages is no less? What does no less mean? No less means bigger. It says don't go to the left of 1600, go to the right of 1600. So because they are sums, again, we build our normal distribution. The mean is 49 times 30.9, which is right here. The standard deviation is root 49 times 9, which is 63. And we're now ready to find the area to the right of 1600. So you come over here, you update the mean to 1514.1, and you go to 63 as the standard deviation. You want to go to the right of 1600, and to the right, okay, you're waiting, it's right here, 0.0863. Again, you want to know, you want to make sure you know which of the two you are going to go for, less or bigger than. So you might inadvertently put 0.9136 when you are maybe in a hurry, but just make sure that you fish out the one that you really want out of the given information. The probability that the sum is at most, what does at most mean? At most means not exceeding. So you're gonna say less than 1595. So I'm gonna go to 1595 here, 1595. And now I'm gonna go for less. Okay, which is 0.90045 right here, 0045. Okay, the 95th percentile for the mean, if the sample size is 65. So first of all, you want to find this new standard deviation. 9 divided by square root of 65 is 1.1163. So if I want to find the 95th percentile, I have to update my mean again and standard deviation. The mean is 30.9, but the standard deviation is 1.1163. And you are looking for the 95th percentile, go for the second option, put the probability in here, 0.95, and say, what is it? 32.73, 32.74. In other words, 95% of all the groups of 65 prostitutes will have an average age of less than 32.74 years. Groups of 65, 95% of all those groups will have an average age less than 32.74. How about the 90th percentile for the sums now? Again, this is going to be 9 times square root of 65, which is 72. So this is a 72. Oh, sorry. Oh, come on. This is what I want to find out. This is 72.56 as your new standard deviation. You come over here, normal calculator. The mean now is 2008, 2008.5, and the standard deviation is 72.56. And you are looking for the 90th percentile, 0.90. These are big numbers again. It has to work a little bit. So you want to be patient with this calculator? Yes, 2101.48 or 0.49. So 90% of all groups of 65 prostitutes will have a sum of ages less than 2001.48 is what we're talking about, right? So this is the central limit theorem. It is the central limit theorem. We use it to track down groups. All you have to know is, how do I use my normal calculator? Okay, what are they asking? Is it the mean or the sum? And then you activate or you update your mean and standard deviation accordingly. Then you use the normal distribution calculator and you're in business. So I want now, unless I don't know whether anybody has a question, I want to go to the homework questions and we scan through a bunch of them so you guys can have a better feel of what really is happening. But maybe you can just have, first of all, have a break. Let us have a break of 10 minutes, then we come back and we try some of these questions in the homework for you, okay? So let me pause the recording and then we'll be right back. Forgot. Well, let us salvage a little bit. I completely forgot to record that. All right, anyway, so that's what we have here. And now part C says, what is the distribution of the sums? The sums, these sums here, also follow a normal distribution. But you change them according to that. So n times mu means what? You multiply n, the sample size, by the, what am I doing? So this is, what is n? N is 46 times 24. 46 times 24. 1104. And this guy becomes root 46 times 2.2. 14.9211. So those are the numbers we're going to pick here. 1104 and 14.9211. So those are three normal distributions. And because they are all normal distributions, you want to make sure you select the right one. In particular, look at part D. It says, if one randomly selected runner, if one randomly selected runner, meaning what? You pick somebody from the population, find the probability that this runner's time would be between this number and that number. So in that case, you're going to use the normal distribution in part A. Use A. Because you are picking a value, one item from the population. So you go to your normal distribution calculator here. Make sure the mean is really the right mean, which is 24, and the standard deviation is 2.2. And you want to be between which values? 11, 24, 11, 24. So I'm going to go for these two values. And I pick 24, 11, 34. And 24, 51, 34. 51, 34. Yep. Then, so that's a very tiny little piece of stuff there. But here it is 0717, 0717, 0717, 0.0717, because they picked one random runner in the population. And then part E, for the 46 runners, find the probability that their average now, their average, meaning that you now use part B. Use the normal distribution in part B, because you are tracking down a group of 46. More than that, you are tracking down the mean of the group of 46. So when I go to the calculator here, I have to change the standard deviation to 0 point something, 0.3244. And for the same lower and upper, I want to find, and I get 3066, 3066, 0.3066. So actually, if you look at the picture, this is why, because the standard deviation was reduced, you now have a bigger chunk of samples within those limits. And yet before, because we are tracking down an individual person, the probability was very, very small, because they are scattered over. The standard deviation was bigger, but now that the standard deviation is very small, more of the information is clustered around there. Okay, and then part F, find the probability that the randomly selected 46 will have a total. Yeah, so the word here is a total time, meaning the sum. So you're going to use the normal distribution in part C, because now we're talking about the sum of more than 1094. So I come over here and I change my mean and standard deviation. Both of them have to change 1104. And I switch this to, what is it? 14.9211. And I would like to go beyond, no less than 1094. So I'm gonna go for the first option. I put 1094.8. And I wanna say, I want this actually, 1094.8. So one more time, these numbers are big, we have to wait for some time. To the left of 1094.8 is 2688. 0.2688. On the calculator. For part E and F, is the assumption of normal necessary? Of course not. Why? We have a whopping 66 runners. So this assumption here was not really that necessary. That's the no, where the sample size is large enough. Part H is very interesting, and I'm glad I remember to record it, because I'd forgotten, but this is very important. Let's read it very carefully. The top 20% of all 46-person team relay races will compete in the championship round. These are the 20% lowest times. This is running. So in other words, whoever finishes earlier is the fastest, isn't it? What is the longest total time that a relay team can have and still make it to the championship round? So pictorially, this is what is happening. Which normal distribution are we going to use? the one for the sum. How do I know what is the longest total? Okay, so we're gonna use C. Okay, what's the mean? 1104. We are saying out of all these competitors, the top 20% are the ones they want to go and continue the next level. So in other words, there's a cutoff number right there where the 20% fastest people are going to be right there. So this is asking for the 20th percentile. I can see the word is top. Depending on what's going on here, top could mean to the other, to the right hand side. But when you are running, when you are racing, the people with this, the lowest, I mean, the fastest people are gonna be the people who finish fast. And that's why we are shading the 20% on the left-hand side. Ordinarily, for other things, we would shade the right-hand side depending on the meaning of what is going on. So I bring up my normal distribution for the sums, which is right there. And I say, I wanna give you a 0.2 here and tell me the cutoff number when you have 20% of the runners. And sure enough, it is going to be 1091.44. So this is 1091.44. To the, is for decimal places or what? 4421. So that's what we have. 1091 44. So this is what is happening. Again, depending on the situation, top could really mean on the right hand side, but in this case, the top means the people who took lower time to finish the relay. Okay, let's check it, and we see what is happening. Of course, that's a given. That is 033244. Yeah, 3244. 1104 and 1492, 11, yes, of course. 0717 is the probability of selecting one person to be running between those two times. 0.3065 is what we got. I think I got 3066. Maybe I overrounded it up. F, what is F? 2688. Yep. And of course, we didn't need the normal distribution. And this is 1091, 4421. That is it. Okay. So this example should really walk you very carefully into this thing. Let me just say something. Let me look at this example, the last part. It says, now this one says that a sticker says great dedication. By the way, it is about each sweatshop worker in a computer factory can put together 4.2 computers per hour on average with a standard deviation of one computer. 14 workers are randomly selected to work the next shift at the factory. Round 4 decimal places, assume a normal distribution. Of course, in this case, it's gonna be a yes. We need to assume normality. The rest of the stuff from A to F, follow what I did in my previous example. You have 3 normal distributions here. The one is already given to you, 4.2 and 1. Then modify them, modify the other 2. But this is gonna be a no. This is gonna be a yes, because you have how many? You have 14 workers only. Now look at part H. a sticker that says great dedication would be given to the group of 14 workers who have the top 10% productivity. What is the least total number of computers produced by a group that receives a sticker? So in this case, unlike shading to the left, you are going to shade to the right, because in this case, if a group produces more computers, then they're going to be working harder. So the more you produce here, the better off you are to be given. I mean, the more likely you are to be given a sticker that says you did a great job. How many computers do you put together as a group of 14? So in that case, you would have to do what? In that case, you would have to look at your normal distribution. And since they are talking of what percentage, the top 10%, this is what is gonna happen here. This will be the top 10%, meaning that this is gonna be 90%. So they are asking for the 90th percentile. That will be the 90th percentile. That will be the only difference that we will see in that question. The rest of the stuff are really the same in content. All right. And if I scan through the rest, they're really the same. They're asking for the 3 normal distribution, the top 10%, great dedication, you know. Again, the top 2% of the groups. All right. So that is what we have here. Maybe I can bring out number 6 here for you before we look at the last part. So here's number 6. This is number 6. The average score for games played in the NFL is 20.5 and the standard deviation is 9 points. 46 are randomly selected, round to 4 decimal places. What is the distribution of the sample mean? Well, this is 20.5, but the standard deviation is going to be 9 over root 46. So 9 over root 46. 1.3270. 1.3270. How about the sums? Well, you multiply 20.5 by the sample size of 46, 943. And the standard deviation is 9 times the square root of 46 again, 61.0410. 041. What's the probability that a sample mean is bigger than 18.8095? Use what? Use part A, because you are tracking down a sample mean. So the mean is 20.5. The standard deviation is 1.3270. 1.327, and you want to be to the left. So I'm going to say one value, and I want 18.8095. To the left, meaning less. So I want this one here, 1013, 1013. Find the 70th percentile for the mean for this sample size, where 70th percentile means you go for the second option. And then put in here a value of 0.70, and it is 21.1959. 21.1959. 21.1959. Okay. Between these two numbers, you go back here. The issue is to know which of the two normal distributions you are talking about. So I'm talking about this very normal distribution. I want two X values. I want 20.0095 and 21.8635. 49.21. Find Q3 for X bar again. Q3 for that thing. You go back here. Q3 means this. 75%. And it is 21.3950. 21.3950. Now it's the sum. Now you're gonna use part what? You're gonna use part B. So use part B now. Use part B. And part B is going to be asking for two different values, the mean of 943 and a standard deviation of 61.041. And you want to go where? You want to go to the right of 888. So first option, 888.237. Bigger. Bigger is what we need. Yeah. Okay. 8152. 0.8152. Is the assumption of normality necessary? No, because one more time, the sample size is bigger than 30. So that's the action going on regarding these problems. And then lastly, the last part of the homework. So start on this thing early enough, guys. Let me go to the last part, which is about the uniform distribution. In other words, if we know that the original distribution is not normal, it is uniform, whereby we have to compute the mean and the standard deviation first. Like number 2 here. This is similar to the example we had before, where we had to compute the mean and the standard deviation of the population. After all, it is not normal. A computer selects a number X from 3 to 11 randomly and uniformly, find to 4 decimal places. So what is the distribution of X? Well, it's uniform from 3 to 11. That is it. Because it is a uniform distribution. Suppose the computer randomly picks 40, what is the distribution of the sample means now? And you know what? In particular, he had to pick a sample size bigger than 30. And that's why you see 40, because the original distribution is not normal. It is uniform. So to ensure the central limit theorem, a sample size bigger than 30, 40 being one such size, was what was selected. Okay, so again, this is a normal distribution. So the mean is gonna stay. So what's the mean? We need the mean now. The mean is gonna be A plus B over 2 . So the mean is 7. Now, the standard deviation of the population is B minus A over root 12. Uh-huh. 11 minus 3 is 8. If I divide 8 by the square root of 12, I get 2.3094. And you know what I do? I have to divide this by root n. So sigma over root n now, this becomes 2.3094 over the square root of 40, because there are 40 numbers picked. And I have 0.3651. And that's what I want. So that's the journey. You want to find the mean of the uniform distribution. You find the standard deviation of that uniform distribution, and then you truncate it accordingly. Divide by the square root of the sample size to determine the standard deviation of the sampling distribution of the mean, as they call it. And now, with this normal distribution, we can find this probability that to be more than 7.5. So I go to my calculator now. I put in a new mean of 7. I put in a new standard deviation of 0.3651, and I want more. So I put 7.5 here. And I say, calculate it. How about 9146? 0.9146. No, more, sorry, that's less. More. Is it more? More than, okay, more than is right here. See, I'd messed up already. 0.854. And that is it. So let's check it and see how far off we are. If we are off 3 and 11, 7 and 3651, yes. And then the probability of having a sum more than 7.5 is 0.854, 0.854 is. Okay. So I believe this should be enough for you guys to go through the rest of the questions. I don't know that anybody wants me to do anything. If there is another example, maybe there's something you didn't understand quite well, let me know. I can pick up another example and go through it if that's what you want. Otherwise, these examples to me, I think should be should suffice for you to check out what is happening. I'm sorry, when I came back, I forgot to press the record button. I think we missed, the recording missed a bunch of things. It missed from here when we talked about the concepts about the central limit theorem. We need a sample size of bigger than 30 if we are not sure about the normality of the population. But if we know the population is normal, this mandate is not necessary. You know, we also had what it meant. It means to have sigma x bar. That's just the notation for the standard deviation of all the means. It means the population standard deviation of all possible sample means, yeah. And then I don't know whether this is where I put up the recording. I don't know where we started the recording, but you know, this is, we have the original distribution, it's normal, and the sampling distribution of the mean will have the same mean. The standard deviation is given right there. We didn't need to assume normality because we had the sample size of bigger than 47. Then we ended up with another example. The sample size this time was less than 30. So this was necessary to assume that the original distribution is normal, just to make sure that the central limit theorem is followed. And I think the others were covered very carefully in the recording. Anybody with a comment? Otherwise, I'll let you guys go. But if you want me to do anything, let me know. I'm still here. All right. So let me stop the recording. And, you know, if anybody has